Welcome to Class 9 in Thermodynamics. Today we're going to talk about heat, heat transfer, and internal energy. All right, so we want to define heat. This is section 3.5 out of our textbook. I'm presuming that you're going to read some of this, so I'm just here to try to be the tour guide and help. All right, so let's read some words off the slide. Heat is defined as the form of energy that is transferred across the boundary. Important words. I will stop here and point out things. Let's see, I'll make little marks. Yeah, I guess go for the pen. The boundary is important things, right? We want to define a boundary, usually for our system. We have a control volume that is made up of control surfaces, and those are the boundaries of the system at a given temperature. Important words, temperature, to another system or surroundings at a lower temperature, right? Here you go, lower temperature. So here are these really important words, right? And by virtue of the temperature difference between the two systems. So one of the crucial things that we need to keep in mind is that heat only moves from a high to a low temperature, right? And always moves from the high to the low. We can't go from the low to the high, and you might be thinking about air conditioners, and yes, okay, or refrigerators. Well, they use a set of systems or set of processes that allow, so there are several processes that are going from high temperatures to low temperatures in order to the overall result of the machine is to move from a low temperature to a high temperature. But generally speaking, for a particular system, a particular process, we can't go from a low temperature to a high temperature. We always go from a high to a low, and you could add this to the list of things. You can't push a rope, and water runs downhill, and heat moves from a high temperature to a low temperature. These are just facts we can't get around, physical facts. And so we consider the heat transferred to a system is considered positive, and heat transferred out of a system is called negative. And heat is transferred from the system at the higher temperature to the system at a lower temperature, and I just beat that horse into the ground. Heat is transferred solely because of the temperature difference. So that's like the driving thing of moving that heat, right, is that temperature difference. And the body never contains heat, because this idea of heat, the Q right there, is it's a transition, right? The heat is something that crosses a boundary. So you kind of we want to think of Q as being something utterly different than the internal energy, right? So sometimes they get confused. Heat has changed, right? It has moved from one thing to another. And it's a transient phenomena, and as we're transferring energy to and from the system. So I'm kind of being repetitive there, but it's important ideas. Talk a little bit about the units, always a good idea. So we usually in SI units we use joules, which is equal to a Newton meter. Sometimes we'll use calories. You're probably used to calories from food. Those are actually kilocalories, by the way. But the calorie is defined as the energy needed to heat 1 gram of water and change it from 1 degree Celsius. And they're being very specific. I don't recall seeing this before, but I guess that is the definition. It goes, if you started at 14.5 degrees Celsius and you got water, right, pure water, and you go to 15.5 degrees Celsius, that in 1 gram of it, that is what the idea of a calorie is. English units for heat, they say foot-pound force. Personally, don't really see that. We can convert that. If you'll recall, I've already used this number, the 778, and if we're going to be very particular, 0.17, these are going to be foot-pounds. So there's the foot-pound force. And this is often called the mechanical equivalent of heat, BTUs, right? So it's BTUs. This is the go-to conversion factor, because that's the most common in the English unit, is to use the BTU. And that BTU is defined as the energy needed to heat 1 pound mass of water at 1 degree and Fahrenheit. And now they're being very explicit here, saying 59.5 degrees Fahrenheit to 60.5 degrees Fahrenheit. So just be aware that when you think of a BTU, it's going back in time, but still used. This is sort of an ancient but still used method. And here's how they came up with it, right, as the definition of what a BTU is, so you can kind of maybe picture a pound of water in 1 degree. And that's very much related to the calorie in the SI units, which gets used sometimes, but not most of the time. We're dealing with joules, or kilojoules, actually. So the process in which there is no heat transfer has this magic word called adiabatic. All right. So anytime you hear adiabatic, what you mean is Q is equal to 0. So we'll keep that in mind. And heat-like work is a path function, and it depends on the path that it takes to get from state 1 to state 2. So like most of the time, you'll see for work, we'll put subscripts, and in this book, they decide to put, so like if you went from state 1 to 2 in work, they go like that right there, and then they do the same thing when it comes to heat. They'll go from state 1 to state 2. It's a path function, and there isn't like any instantaneous heat because it's between two states. Right there, oh, I made a little thing. And right, so that's what also, for that small increments of heat, we use this del symbol. This is the inexact differential. I think is this enough for a video? I guess so. Oh, other things I might want to mention, and then we'll make a new video for the heat transfer. Other things I would want to say. Let me move over to this. Let's see, I haven't got that squared up just yet. Quite often, what we will do with this Q right here, we will use small q, and that'll be on a per mass basis, right? And that's really useful because a lot of times we were going to want the heat rate, which is going to be q dot. So one instance where this happens is we might take the flow of mass, the mass flow, times this small q. So this is sort of like interaction, right? So this is the amount of heat, this is the amount of heat per mass, and then here is the heat rate, right? So here's the flow of heat. Here's how fast or slow it is moving into or out of a system. So these interactions are kind of important. Heat rate. Remember that this is like an energy, right? This is a form of energy transfer. And a lot of times we will call it heat transfer, and that's the important thing. Right? We're talking about a transfer from one state to another, as opposed to U, right? So recall that we had said that the change in U is going to be equal to Q from 1 to 2 minus W from 1 to 2, right? So the change in internal energy for a system, right, for a particular amount of mass is going to be equal to the heat, and this is in, and this is defined as out. So by the way, some books will write it out this way, which is maybe a little easier to keep track of the thing. I'm not doing the 1 to 2. I'm just going to go from in. We'll go Q in minus work out. And this is also often, this convention with this negative sign, you can imagine, is often what a heat engine is, like the Stirling engine that I used in my coffee cup, if you recall, right? They put this on top of the coffee cup, and the difference between temperatures right here, which is what drives heat, that right there, that turns into mechanical work, right? So often it's heat comes in and work goes out. That's like the most typical situation. It doesn't have to be that way. We could get work we could put work into a system, and we can take heat out of the system. So just be careful with the signs right there. So that's enough information for one. We're going to talk about heat transfer, which is just a topic in this course, but there's an entire course in heat transfer that mechanical engineers at least will be taking. So we're going to just briefly touch on it.